Hello, fellow chemists. Jolly here. Today we are going to be discussing molecular geometry, which basically means molecular shape, and we're going to talk about two different theories. Now, this video is only going to talk about the first one, but there will be a later video that talks about the second. And the first one is called valence shell electron pair repulsion theory, and yes, that is a mouthful. So, valence shell electron pair repulsion theory, and it's lovingly called VSEPR. It's lovingly called VSEPR. So, valence shell electron pair repulsion. Now, the key word in here is repulsion. So basically, we are going to look at three-dimensional space and how close things can be together and still be the optimum distance. So basically, they're repelling each other and they're trying to take up three-dimensional space. The other theory that we're going to talk about is called hybrid orbital theory. This also takes into account the shapes of different molecules, but in a different variation. It uses atomic orbitals. Okay, so we're going to talk about hybrid orbital theory in the future, but we're going to jump right into VSEPR theory. And VSEPR theory is based on 3 dimensions. So we want to have 3 dimensions with the least amount of interactions, or if you will, repulsions. Alright, so we're going to put 2 things around an atom, and the best way to put 2 things around an atom is 180 degrees apart, and that is called linear. Okay, so it's 2 things. Now, there's a jollyism or a jolly term. I call it family linear. Okay. All right. The next one would be 3 things around it. So 1, 2, and 3. Oh, well, that makes kind of a triangle. So that's going to be 120 degrees, and it has 3 things. And it is called trigonal planar. The reason it's called trigonal planar is because it's flat, which means planar, and it makes a triangle. So basically, it is a flat triangle. That's where the name trigonal planar comes from. All right, now 4 things is going to start to get interesting because I can't stay flat anymore. So 4 things, I'm going to have to put 1 straight up, 1 kind of out, and then I have to add in some true 3-dimensional pictures here. If I do dash, 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 that means it's behind the plane. And if I do a wedge, that means it's coming out of the plane or in front of the plane. Now these angles, in any direction, will all be 109.5 degrees. This family is called tetrahedral because it has 4 things around it. All right, so that's with 2 things, that's with 3 things, and that is with 4 things. And I'm going to clear this page so that I can do the last two. Alright, so I had 4 things before, now I'm going to put 5. Now I'm really going to start crowding, and we're going to break it up into locations. So I am going to have this vertical location, what I like to call the axis, and since there's 2 of them, the axes. And then I have to put some around it in the equator or the skirt. Okay, I just like to use the term skirt, it's very visual. Alright, I'm going to dash that back, and I'm going to give 2 wedges here, or I could have drawn it this. Or I could have drawn it like this. Okay, I want you to take a close look. All of those things are identical. They are all identical. All right, let's talk about these angles then. So the vertical, or the axes, and then here, I would call that, in the skirt, in jolly terms, or if you will, the equator. Here, that's just like family linear, and that's 180 degrees apart. This is family trigonal planar, and so it's 120 degrees apart. But what's interesting is we have this new angle. What about from the axis to the skirt? And that is only 90 degrees. So let me label over here again. This right here and this right here. Okay, so from the axis to the skirt is 90 degrees. The skirt itself is 120 degrees. And anything from up here to the skirt is 90 degrees. So that is there, here, here, or there, and then getting a little messy, but there from behind. So this one has 3 different angles. And what in the world is it called? It is called trigonal bipyramidal. And it has 5 things around it. And look, I made a mark. Now let me explain to you where that name comes from. That name comes from the actual shape if I was to draw a face on it. So I'm going to draw it again here. So if I was to put a plane or a face on it, there's one. Okay, now I'm doing the one behind. Let's go back to there and back to there. And so that one would be green. And then this face would be blue. So do you see there's 3? So there's my triangle. But guess what? There's one on the bottom too. So you have, okay, you really can't see the bottom one. That looks bad. But down here, there is 2 pyramids sitting on top of each other. So the bi stands for 2. The pyramid is the shape. And what, if you will, geometry is it in? It's a triangle. So it's a triangle pyramid, and there's 2 of them on top of each other. That's the name trigonal bipyramidal. And then, of course, there's those angles. All right, let's look at the last one. Let's look at octahedral. Nope, don't want blue. Let's put one thing in the center, and then 1, 2, 3, 4, 5, and 6. So again, these mean they're going behind you. These mean they're coming at you. And there are 6 things around it, and this is called octahedral. Or in my terms, family octahedral. 6 things. All right, now what kind of angles are we talking about here? Well, I could draw it this way, or I could draw it that way. Okay, take a look. Those are the exact same picture. I'm just rotating a little bit in space. And the angles here, from axis to axis, that is 180 degrees. If I go from the axis to the skirt, that's still 90 degrees. But notice here there's 4 things in that skirt, and so there's 2 different kind of angles. We have from one piece to a piece that's adjacent in the skirt, that's 90. But if you go from the extremes of the skirt, that's 180 degrees. Another way to picture that is, this is one piece of it. Okay, so there's the skirt. There's the skirt. That's 180. That's 90. That's the skirt. And then there's one coming at you, and there's one going behind you. That's what this picture of octahedral looks like. Huh. Well, that's pretty interesting. Let's see if we can actually play with them. So if I took family 1, and I'm going to call it family linear from now on, if I took that, both of these have to be bonds. Okay, so that's the basic definition. These have to be bonds. What if they're not both bonds? What if I had something like this? One side was in a bond and one side was in a lone pair. Well, now I have to give you shape. So everything I've given you right now has been completely full of bonds. That's why I call it the family. But I'm going to start taking away some of those bonds and putting, if you will, a lone pair or something that would repel. So lone pairs are the easiest. And then we're going to see what kind of shapes come out. All right, so for family linear, what are my possibilities? Well, the maximum, and I'm going to put two terms here. I'm going to put the family, but I'm going to put how many are in bonds and how many are non-bonding. And in this case, I always use lone pair. Okay, so I call it family 2 or family linear. And I'm going to have 2 bonds, so that's this one. And so no non-bonding. And so what is the shape? It is also linear. Okay, so right here, either of these terms mean the same thing for me, linear or family 2. All right, well, let's do a variation. What if I do family 2, but I do 1 bond and I do 1 non-bonding? So I'm talking about this. What is this angle still? Oh, that's not a bond. It's still flat, so it's still going to be shape linear. It's still going to be shape linear. All right, let's go to the next one. What if I have family trigonal planar? All right, so my family is trigonal planar, and my bonding, my non, and my shape. Okay, if I have 3 all in bonds and no non-bonds, well, it's the same. Or we could say family 3, by the way. Okay, what if I have family 3 or family trigonal planar and I have 2 bonding and 1 non-bonding? Well, what in the world would that be? Okay, so I'm asking about this. Keep in mind, the bonds only deal with the actual bonds and the angles between them. So yeah, this is still 120, but do you see that shape does not look like a triangle anymore? Because the shape only describes the bonds. Okay, yes, I know that's there, but this is the shape I'm describing, and it looks bent. It looks bent. Well, what if I have only 1 bonding and 2 non-bondings, but I'm still in family 3 or family trigonal planar? Well, what in the world does that one look like? Remember, the shape comes only from the bonds, and look, we're back to linear. All right, so before we go on, let's actually look at some examples. Let's look at some examples. All right, now I know ionics don't usually get drawn with Lewis dot structures, but I'm going to draw this one just because it's a nice visual. All right, find the center of the molecule if possible. Okay, so there's my center. How many things are around it? Now remember, a thing is either a lone pair or a bond. So a thing, in Jolly terms, it can be an actual bond. But remember, there are 3 types of bonds that you know. You know singles, you know doubles, and you know triples. So a single bond is one thing, a double bond is one thing, a triple bond is one thing, or we could also be talking about lone pairs. All right, So when I said how many things are around beryllium, there's one, and there's one. Now these lone pairs belong to fluorine, and I'm talking about beryllium. So there are 2 things around it. So what family is 2 things? That is family linear. And there are 2 bonds and no lone pairs or no non-bonding. So what is the shape? The shape is also linear. Right, let's try another one. How about carbon dioxide? All right, find your center. That would be the carbon. And how many things are around your carbon? There's a double bond on this side and there's a double bond on that side. Yes, it's still just a bond though. So there are 2 things. And so again, I have 2 things. They're both bonds, so there's no non-bonding. So it is again shape linear. Well, let's keep going. What about carbon monoxide? That's a lone pair. All right, this one doesn't have an obvious center, so you just choose one of the atoms. You could talk about the shape at each location. We're going to talk about carbon first. So at this carbon location, how many things are around it? Well, there's a lone pair and there's a triple bond. So do you see there's still only 2 things around it? But one of them is in a bond, one of them is in a lone pair, but still it's flat, so it's still called linear. Well, what about at the oxygen? Well, we'd get the same answer, because the oxygen has a triple bond and a lone pair around it, and we'd come up with the exact same answer. But that is how you would look at linear. But we're kind of limited to our shapes because you get linear. Let's go to trigonal planar. So here's our original. We know it's 120 degrees, and so this is family trigonal planar. We know, if you will, the things. I need to know bonding, non-bonding, and shape. Okay, well, if I have all 3 things, it would be trigonal planar, 3 things, 3 bonds, no non-bonding, so it is still called trigonal planar. What if I had this? Now remember, the shape, the name of the shape only comes from the bonds. And do you notice there's only 2 bonds here? So it's making this kind of a shape. Oh, I look bent. Okay? And so we are still family trigonal planar, or family 3, but the difference is I only have 2 bonds and I have 1 non-bonding or 1 lone pair, and so this is now called bent. Is it still 120 degrees? Yes, it's still 120 degrees, but its shape now, because of the bonds, are called bent. Well, let's keep going. What if I had this? Oh, look, it's still family trigonal planar, still 3 things, but the problem is I only have 1 bonding and 2 non-bonding, and the only thing that's giving me my shape is 1, so I'm back to linear. I'm getting it. Are you seeing my trends going on here? Now, how about those angles? I told you before that this was 120 degrees. Well, that is also true here, except lone pairs tend to take up more space. So I could say maybe this got squished. Whoops, not this one. This one would be a little bit more. I could say this angle would be a little bit more than 120, and this angle would be a little bit less than 20. I couldn't give you an exact amount, but I could tell you that it got squished just a little bit. All right, so there is family trigonal planar. What are some examples of family trigonal planar? Well, one of my favorites is BF3. Oh, look. All right, find your center, which is the boron. How many things are around boron? Oh, well, let me check. There's one thing, there's two things, and there's three things. All right, you are in family trigonal planar. How many of those things are bonds? Do you see I'm right here? 3 of them are bonds, and none of them are non-bonding, so this shape is called trigonal planar. Well, can I do another one? Sure. Just a little side note, if you are not understanding these Lewis structures, you need to go back and really work on that Lewis structure section because it has to be just instinctive. Keep in mind, you might not be able to do it as fast as I can do it, but you need to be able to get those Lewis structures fairly quickly and be confident that you have the right one. Other words, your shape is going to be wrong because you didn't draw the correct Lewis structure. All right, so let's see. How many things are around the center? And the center is sulfur. And so I have a lone pair, I have a double bond, and I have a double bond. So I have 3 things. So I am in family trigonal planar. But I am now in this category. I have 2 in bonds, and I have 1 in a non-bonding. So the area right here, okay, this area, what does it look like? It looks bent. It looks bent. All right, well, let's do our last variation. What about, oh, I don't know, diatomic oxygen? Again, find your center, and there's no obvious center, so just look at one of them. And this oxygen has, well, we'll do this way. That oxygen has 1, 2, 3 things around it, so I'm in family trigonal planar, but only one of them is a bond, and 2 of them are non-bonding or lone pairs, and so this shape is linear, because remember the shape is about the bond. And if you look at the other side, it's going to be identical. I have 1, 2, 3 things, and it's going to be 1 bond, 2 non-bonding or 2 lone pairs, and it's also going to be linear. All right, well, this is getting fun. Let's go to family 4. All right, now, could I draw it like this? You bet. Could you draw it like this? You bet. Do you see? It doesn't matter as long as you stay true to the 109.5 degree angle. That's really all that's important. Just these 2 are the most common of how it's drawn. Okay? All right, so we're going to do the same thing. We're going to have a family 4. So, and I keep putting them in different orders, but it's all the same material, or same ideas. So how many things? What is its family name? This one would be tetrahedral. Family tetrahedral has 109.5 degrees. How many are bonding? How many are non-bonding? And what would be my shape? All right, let's take the first one. Let's take carbon. We're going to put some hydrogens around it. And let's say we drew this, and that is our Lewis structure. Beware, 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 beware. I cannot not emphasize this enough. It is flat for convenience only. All right, let's see if we can figure that out without seeing in 3 dimensions. Well, how many things are around your center? Well, I have 1, 2, 3, and 4. What is the name of family 4? It's tetrahedral. Well, what angles are always in tetrahedrons? They're 109.5. Well, no, Jolly. Look, that looks like 180 degrees to me. And that looks like 180 degrees to me. And this looks like 90 degrees to me. And that looks like 90. No! Okay, it is drawn flat for convenience only. I should have drawn it like this. But that gets kind of hairy when you're doing the original, so it's okay to draw it this way. as long as you recognize it's for convenience only. This is really that. Okay, so I have 4 things around it. I have 1, 2, 3, and 4. And I have 4 bonding. I have no non-bonding, so my shape is just like my family. It's tetrahedral. What about the next one? Let's take a look at ammonia. It's drawn flat for convenience only. All right, how many things are around your center? 1, 2, 3, and 4. So it is in family tetrahedral. But this time there's only 3 bonding and 1 that's a lone pair or a non-bonding. So what kind of shape is going on here? Well, the best way to show you that is to redraw and exaggerate a little bit. Do you see it almost looks like a pyramid? And the pyramid, the base is here on the ground, and then the lone pair is at its apex. So this one is called, you're going to love this one, trigonal pyramidal. Or pyramidal, whichever. How come it's not called trigonal bipyramidal? Because there's not 2 of them. Okay, I only have 1 pyramid with 3 sides, so it's called trigonal pyramidal. And what about those angles? This does take up a little bit more room, so it pushes. So I guess those would be a little bit less than 109.5, but not a ton. All right, so that's trigonal pyramidal. And that could also be drawn like this. That is a 3D representation of it. All right, we have 3 bonding and we have 1 non-bonding. Can I come up with an example for the others? You bet. I hope you're finding this a little bit exciting. Oh, shapes of molecules. This is just too exciting because once you know how to do the shapes, you can predict physical characteristics and you can start to literally look at bonding, and it's just going to open the world of chemistry for you. So let's look at water. Oh, I love water for so many reasons. Oh, look at my little water. Now, I could have drawn it like this. There is absolutely no difference between those 2 drawings, but one's a little deceptive. All right, how many things are around that oxygen? I have 1, 2, 3, and 4. So I have family tetrahedral. How many bonding do you have? Well, I have 2. How many non-bonding do you have? Well, I have 2. So what is my shape? It's harder to see from this one, but remember the shape is only dealing with the bonds. Oh, I've seen that before. That is bent. This is still bent, but do you see it's hard for me to draw when it's in this way? What are my angles? 109.5. I don't care that this looks like 180 because it's not. It's still 109.5 regardless of how I draw it. Now, there are 2 lone pairs, so I can say that this is going to be a little bit less, okay? So here I could say that one's going to be a little bit more, and right here, do you see it's going to get squished? It's going to be a little bit less than 109.5. And water is around 107 degrees. It's around 107 because those 2 lone pairs take up more space than you would expect. All right, well, we have another variation. What if I go all the way down to, I don't know, can I get down to just 1 bond? You bet you can. A little bit silly in hindsight, but... Huh. How many things are around chlorine? 4. 1. Whoa, I want red. 1, 2, 3, 4. So I'm in family tetrahedral, but I have 3 sorry, go in the other direction. I have 1 in the bond and 3 in the non-bonding, and so what is my shape right there? Well, I'm back to just one thing. So it's linear. All right, and that is family tetrahedral. Family tetrahedral. I wonder who's coming next. Family trigonal bipyramidal. All right, so how many things? It's family name. How many are in bonds? How many are in non-bonding or lone pairs? And then what is my shape? Now there's going to be more variations here. Let's start with the first one. And I like PCL3. Not PCL3, sorry, PCL5. Now notice I'm drawing my Lewis structures already with the shape in mind. You might have ended up with this. In fact, you probably did end up with something like this. That's probably how you ended up with your Lewis structure. I was just seeing the shape. So let's go off this one. Find your center. How many things are around it? 1, 2, 3, 4, 5. So it has 5 things. That is called family trigonal bipyramidal. How many bonds does it have? 5. How many none, so it's the same name. Alright, variation on a theme. What if I was to lose one of them? What if I was to lose one of them? Alright, let's see. Put an example in here. Let's do SF4. Whoa, that's an ugly F. Alright, how many things are around it? I've got 1, 2, 3, 4, and 5. So I'm still family 5. I'm still family trigonal bipyramidal. I have got 4 bonds. I've got 1 non-bonding. So what kind of shape is this going to leave me? This one, you're going to love this one. This is called the seesaw shape. This is called the seesaw shape. You're going to love the visual. Okay, if I take my sulfur and it's sitting in the center, I'm going to give it 2 legs, and that's going to go to the ground. And then guess what else is there? There's 2 more, and this is the little teeter-totter place, or the seesaw place. This is where you would sit. So it looks like a seesaw, and yes, that is the reason. And remember, 2 of those have to be out of the plane. And that's where the name seesaw comes from. It's just a visual. Who says chemists aren't original? Alright, so we've looked at 4, and now can we go further down? And the answer is yeah. It's going to be harder to even see that shape though. So let me get rid of these. Alright, what about this molecule? ClF3. 1, 2, 3. Now that looks like trigonal planar right now, but don't forget chlorine has 7 valence electrons. Alright, now the visual on this one is a little bit harder, or I don't know, maybe it's easier. But I always saw it as a great big T. Yes, it's called T-shaped. So I have 1, 2, 3, 4, and 5. So I have 5. I'm still trigonal bipyramidal. I have 3 bonding, 2 non-bonding. This is called T-shaped. Oh, wasn't that fun? Wasn't that fun? So that's a 3 and 2. Can I keep going? Yes, I could. Alright, so my next variation would be, what about 2 and 2? And I'm going to go all the way up to xenon for this one. Woohoo! How many things does xenon have? 1, 2, 3, 4, 5, and 6. And that is not the one that I was supposed to be doing. Sorry. I was going to jump to XEF2. Alright, hold on. Getting a little ahead of myself. Can't jump families here. XEF2. So 1, 2. There. There's xenon with just 2 fluorines. How many things are around it? There's 1, 2, 3, 4, and 5. So I'm still family 5. I'm still family trigonal bipyramidal. I have only 2 bonds now. I have 3 non-bonding. And can you kind of see that shape? Okay, is it kind of singing to you? It goes back to linear. It does go back to linear. All right, now, wouldn't it be more, I don't know, energetically favorable to put 2 of the lone pairs in the linear and to make the bonds kind of bent? There is a whole area of chemistry where we can talk about the optimization, but if you will, for our purposes, will you just see those bonds as linear apart from each other? And then what would happen if I went all the way down to only 1 bond and 4? Well, it would still be linear, because then we would only have 1 bond. And that is family 5, trigonal bipyramidal. All right. Family octahedral. 1, 2, 3, 4, 5, and 6. So how many things do I have around it? It's family, the bonds, the non-bonding, and the shape. Now, I'm not going to give you all the shapes, even though they do exist. We're going to start with just a few of them. All right, so how many things are around it? It's 6. The family is called octahedral. So if I have all 6 bonding and none of them non-bonding, I would still get the shape octahedral. And a great example of this is SF6. Are you recognizing my little flub from before? I drew an octahedral instead of a trigonal bipyramidal. Okay, how many things are around your sulfur? 1, 2, 3, 4, 5, and 6. So it's family 6, and 6 are bonding, and there are no non-bonding, so it's octahedral. Well, what if I was to get 1 lone pair? What if I had 1 lone pair in there? Let's try that. It's going to be iodine. And who should we put around iodine? Fluorine is our crazy one. All right, how many things are around your iodine? We've got 1, 2, 3, 4, 5, and 6. But this time, I only have 5 in the bonding. I have 1 lone pair. And so this is a crazy one called square pyramidal. That's not square pyramidal. Hold on, let me look at that. Oh, yes it is. Square pyramidal. I was saying one thing and visualizing another. What in the world is a square pyramidal? Easy. Make a pyramid and the shape is going to be a square. So I'm going to exaggerate this just a little bit. My lone pair's at the apex. And do you see the base is going to be the shape of a square? So it's a square pyramid is what 5 bonds and 1 non in the family octahedral is. And then our last one that we're going to play with, we're not going to look at those other variations. We're going to do this one. What if I had, oh, who should we do? Let's do Xenon with, this is the one I drew before. Got all carried away. I can't stress enough, if you don't have a correct Lewis structure, it is going to lead you down the wrong path. Alright, Xenon has 1, 2, 3, 4, 5, and 6 things around it, so it is family 6, which is called octahedral. 4 of them are bonding, 2 of them are non-bonding, and now do you see that the best arrangement of those two things, I need to get them as far away from each other as possible. Those are going to be 180 degrees. So do you see the 4 fluorines are going to go in the plane? They're going to be squished into a square. And this one is called square planar. So that one is called square planar, because the best way to get those 2 lone pairs away from each other is to put them on opposite sides, which is 180 degrees, and everybody else is squished in the skirt, and it looks like a box or a square, and it's flat, so square planar. That is how you determine molecular geometry using the VSEPR theory. Now keep in mind the term things and the term family. Those are kind of jollyisms to make it a little bit easier. There are technical terms that talks about the electron and the pair repulsion. I like those because it's a more visual representation. Alright, you should be able to come up with every shape from a Lewis structure that you have drawn, and in the future you will start drawing your Lewis structures with those shapes and those angles in mind. So really quick, just as a review. Nope, wrong. I have this for you. It is not in my cheat sheet, okay, but this is in my notes, and of course in some variation it's in almost every textbook. Ta-da! Oh, look. Alright, so let's kind of take what I was talking about and put different terms to it. So these are your electron pairs, or your spots, or your, if you will, things. How many things do you have? Well, here's your total, okay? So that's going to be your family. So I link these two together. So if you have 2 things, you are family linear. If you have 3 things, you are family trigonal planar. 4 things, you are family tetrahedral. Okay, so to me, those 2 things are synonymous. Let me get rid of those now. What about this going on in here? Bonding means it's in a bond, and the lone pair, just like we've been doing, means lone pairs of electrons. And so if you have 2 and 0, you would be called 180, and here's the examples that I did for you. So they'd be 180. If you had 1 and 1, well, you're still family linear, still shape linear, and it's the carbon monoxide. All right, if you're in family 3, which is trigonal planar, 3 and 0 would be 120 degrees, but 2 and 1, remember, has that lone pair on top, and so the angles, they look bent to each other. So the actual shape or the geometry is bent. All right, and then if you get down to only 1 bond, well, of course, you're back to linear. And then we've got tetrahedral. So we have, everybody's accounted for. 1 lone pair, 2 lone pairs, and 3 lone pairs. And notice I said approximately 109. Remember, water really squishes those 2 lone pairs, and that's around 107. And then trigonal bipyramidal. I listed all the angles here, but you do have to know their locations. Okay, so beware. You do have to have a visual on their locations. But trigonal bipyramidal, seesaw, T-shaped, and linear. And then I only give you 3 for the octahedral family, which is octahedral, square pyramidal, and the square planar. And that is somewhere in a text. You could make your own. I give everything but this. Okay, so I don't give the whole thing in my reference sheet. I only give the other side, so I don't give away what the angles are. You would have to know that. All right, molecular geometry. Oh, look at the power you have. Power visualization, and we're going to start to apply that to chemical and physical characteristics. So until next time, Jolly out.